So good morning. My name is Mike Oristaglio. I'm Executive Director of Yale Climate and Energy Institute, and I would like to introduce the director, Mark Pagani, Professor of Paleoclimatology at Yale University, who will say a few words to welcome you to our conference. Mark?
All right, hello folks. I don't want to take up too much of your time here, but I do want to welcome you to our conference, and I do hope we all learn something. So I'm a climate scientist, I suppose, and I'm deeply entrenched in, the history of climate in the past and also projections for the future. And if you're following the science of climate, you'd know that in the next 100 years, we're projected to reach CO2 levels not seen for the last 50 million years. 50 million years ago, we like to refer to the Earth as experiencing a super greenhouse climate. That's a climate where there's subtropical and tropical flora, ecosystems at the poles. And there's palm trees on Antarctica. We're not going to get there that quickly, but that's where we're headed. Okay. Without question, CO2 is the most important greenhouse gas on Earth, and it has a tremendously long half-life. Extraordinary. Thousands to tens of thousands of years. Whatever we put into the atmosphere today will last for thousands to tens of thousands of years. And coal-based energy production contributes to hundreds of thousands of deaths globally, as estimated by the World Health Organization. So for me, CO2 really is the enemy, and anything that lowers the rate of CO2 emissions and contributes to CO2-free energy should be a priority. Globally, nuclear produces about 11% of electricity, and in the US, it's 19%. And it's already an important part of the climate solution. But it's also very taboo, and certainly around my dinner table, okay? But how much of the discussion on nuclear energy around the dinner table is based on outdated information, mythology, and poor information regarding our options it's important to discuss. So the goal of the conference is to have a mature conversation on new technologies, the existing problems, and possible solutions, and perhaps a vision forward. So again, I hope we all learned something from this today. One last thing. The conference was spearheaded by two members of the Yale community, Professor Yahia Khalil and an undergraduate student, Jared Milford. Now, Khalil is a professor of chemical engineering. He was recently appointed as chairman and operating agent for the Hydrogen Safety Task of the International Energy Agency. He was part of the U.S. nuclear risk assessment teams that developed accident management guidelines to address vulnerabilities of the U.S. nuclear fleet after the 1979 Three Mile Island accident. But in some ways more interesting, the conference really began with Jared Milford. He's an undergraduate, as I said. When he came to my office to discuss nuclear energy, he majors in ethics, politics, and economics, and he's really the lead organizer of today's conference. I'm sure you all, the participants, have interacted with him quite a bit. He's worked at the Brookings Institution on Energy and Climate Policy and has been a fellow at Yale's Institute for Social and Policy Studies. And before coming to Yale, he worked at the Reed Research Reactor in Portland, Oregon, where at age 17, he became the youngest licensed nuclear reactor operator in the nation. Now, I don't know what you were doing at 17. I know what I was doing at 17, and it didn't come close to that. So with that, Michael, come on back up and introduce the game rules here and make your introduction.
Stand there for a second. So Mark is an academic, climate scientist. I'm from the energy industry. Can you tell the difference?
There's a difference. Yes. and we work through our
Climate and Energy Institute. Okay, so we will start the agenda with the opening address on climate change and the urgent need for abundant carbon-free energy. Jim Hansen, who is the director of the program on climate science, awareness, and solutions at Columbia University, wanted to be here for this talk. At the last moment, literally, something came up that required him to be elsewhere. He sends his regrets, but more important, he sends his deputy director. So I would like to introduce Dr. Pushker Kharecha, who has kindly agreed to give the talk on Jim's behalf. Dr. Kharecha is a climate scientist himself. He worked for several years at the NASA Goddard Institute for Space Studies, where he has worked on climate modeling, in particular the interaction between human influence and climate. And he continues that work as the Deputy Director of the Program on Climate Science Awareness and Solutions at Columbia University's Earth Institute. So please welcome Dr. Pushker Kharecha.
So I should just click on the keyboard?
Yeah, you can click on the keyboard to advance.
Is it a
Here's the
pointer?
pointer.
Okay, good. Thanks. All right. So thanks a lot, Mike and Jared and the other organizers for accommodating this last-minute substitution. As Mike said, Jim sends his sincere apologies, and I'm also sorry that for those of you who were expecting to talk with him or were excited to see him, hopefully at least the message will still be more or less the same. I didn't have much time to prepare for this, but luckily, as some of you might know, almost exactly 2 weeks ago, we held a very similar meeting, a one-day meeting at Columbia. It was under the auspices of the UN Sustainable Development Solutions Network, and I was the lead scientific organizer of that. So, and Jim and I both gave talks there. So what I'll be presenting here today is more or less a hybrid version of both his and my talks. So, all right. So I'm just going to cover two broad topics. Since this is a general audience, I'm going to run through briefly the causes and effects and remedies of recent climate change, and the historical and potential future role of nuclear in mitigating climate change and air pollution. Okay, so when I give talks about climate change, I usually like to cover three key aspects. First of all, they're loosely modeled after the three working groups of the IPCC. First, how do we know climate's changing and that humans are mostly responsible? And second, why should we care? In other words, what are the likely impacts of unabated climate change? And third, what can we do about it, and what's the required time frame? Okay, let's start with the global mean surface temperature data, and I'm sure most of you have seen these types of graphs, so I won't go into too many details about them, but basically the time series up at the top tell us that most of the global surface temperature change over the entire industrial era has occurred in the last few decades, and the spatial data shown here tell us that the polar regions have warmed the most, and that the land regions have warmed more than the ocean, the northern hemisphere has warmed more than the southern hemisphere, and so on. We also know that nighttime temperatures have increased faster than daytime temperatures. And lastly, we also know from satellite measurements that tropospheric temperatures have increased while stratospheric temperatures have decreased. Troposphere is the lowest layer, stratosphere is the next lowest layer. And this is all fully expected from theory. Now, there's been a lot of attention recently on the slowdown in the rate of global surface warming over the last 15 years. And you often hear this invoked, usually by climate change deniers and minimizers, as evidence of the absurd notion that climate change stopped in 1998. That's immediately falsified by recognizing a few basic facts. First of all, keeping in mind that this is only one line of evidence, and it's not even the most important one, actually. And second of all, a much more useful insight into the problem is gleaned when we look at the planetary energy imbalance. So the planetary, it's defined as the difference between the absorbed radiation and the outgoing radiation to space. And it affects all components of the climate system, so not just the air, as shown in the previous figure, but the land and most importantly, the ocean. And when you do the type of analysis we did a few years ago, and many other groups have done similar analyses, we all find that over 90% of the overall climate system heating has taken place in the ocean. And that's again fully expected from theory because of the very large thermal inertia of the ocean. And we also know that the imbalance was significant and it persisted even during the period of the most recent unusually prolonged solar minimum, which is highlighted here. So this, combined with other lines of evidence that I won't go into, tell us very strongly that the sun cannot be the primary cause of the recent energy imbalance and therefore recent global warming. Now, there's also important indirect lines of evidence of global warming. Oops. And probably the most important category of evidence is the net loss of ice around the world. Now, this figure shows the net mass loss from the two great ice sheets, Greenland and Antarctica. And when you look at the numbers, it adds up to several hundred gigatons of ice per year over the last decade or so, combined over the two ice sheets. And this amounts to about a third of recent global sea level rise. And that is very significant and very troubling, because the most vulnerable parts of these two ice sheets, if they fully disintegrate, they could amount to about 10 meters of global sea level rise. And as Mark was saying, to get back to a planet like that is basically just a completely different state, completely different point in time. It's like we'd be living on a different planet, not to mention the massive, massive coastal disruptions around the world and so on. So the bottom line, again, I glossed over tons and tons of material, but as far as causation, the observed rate, magnitude, and spatial patterns of recent climate system warming, overall climate system warming, not just the surface, not just the land, and so on, along with well-established scientific principles, which is really what we mean by theory in science, as opposed to theory in law is more of a speculative term, but combined with results from climate models, they allow us to rule out natural factors, and they show that the enhanced greenhouse effect is actually the prime, by far, the most important driver of climate change in at least the last 50 years. I guess this thing just has a mind of its own. It just keeps going, which is fine. But so given that, the next question is, what is the cause of the enhanced greenhouse effect? Well, multiple lines of a very strong scientific evidence show that human activities, most importantly fossil fuel burning, secondarily land use, are fully responsible for the rise in CO2 and other greenhouse gases over the industrial era. So for better or worse, we basically now control the fate of the Earth's climate. So taking a closer look at fossil fuels, so the figure on the left shows the total primary energy supply by source, and you can see that over the past several decades, fossil fuels remain by far the dominant source of global energy supply. They account for about 80% of global energy. And on the right here is a figure showing fossil fuel CO2 emissions over the industrial era. And we see that despite the impressive growth of renewables and nuclear, in some countries at least, CO2 emissions are continuing to rise exponentially. In the last decade, for instance, they've risen by about 3% per year. And so the upshot of all this is that fossil fuel use is responsible for about 80% of the atmospheric CO2 rise. Remember, the other component is land use. So what are the consequences that we've already seen from human-induced climate change? Well, one of the big ones is sea level rise. And this is very important because this is essentially irreversible on millennial timescales. In other words, what we're seeing is the sea levels now are going to be the baseline sea levels for millennia into the future. So what this figure shows is that the rise in the last 20 years, which is the period of most reliable data, this is mostly gleaned from satellite data, the rate of sea level rise is more than double the rate over the previous 60 years, and is more than 5 times the rate of the early 20th century. So sea level rise is accelerating. And a higher sea level, among other things, it means more damaging storm surge, as we witness here on the East Coast with Hurricane Sandy. We're also seeing, in terms of consequences, a worsening of extreme events, extreme climate-related events in various parts of the world. These include heat waves, wildfires, and storms, droughts, and especially here in the U.S., increased frequency and intensity of heavy downpours and floods. Okay, so what about the future? Well, all right, so in terms of sea level rise, a good place to seek guidance is the Earth's history. So if we look at the previous interglacial, which was the Eemian interglacial, it was about 120,000 years ago, the global average sea level was between 5 to 9 meters higher than it is today. Remember, a meter is just over 3 feet. So, and that was when the temperature was at most 2 degrees Celsius above pre-industrial. So that's very important to bear in mind when you hear discussion, which you will, especially come as we get closer to December, the Paris Framework Convention talks. 2 degrees Celsius is by no means a guarantee of safety. In fact, Jim and I and a growing number of colleagues are calling on the community scientific community to be more outspoken in saying that there is not a scientific consensus about 2 degrees Celsius. That's more or less a political number. And as far as what would happen if we go beyond 2 degrees Celsius, just say 3 or 4 degrees Celsius above pre-industrial, which is where we're headed, or even worse, we look back to the Pliocene epoch, and that was several million years ago, and we see that the sea level at that time was about 15 to 25 meters higher. And so either one of these, even the low end, relatively low end, even 1 meter of sea level rise, it would be very disruptive to coastal communities around the world. And when we're talking about these levels, I mean, there would be massive disruptions to coastal human communities and ecosystems, including very populous areas, and it would disrupt, at the very least, hundreds of millions of people's lives. Okay, what about another irreversible impact of human-induced climate change, which is species extinction? This is a nice figure. I like this. I've been using this for a few years, even though it's from the previous IPCC report that came out in 2007. The recent one, I haven't seen a similar figure like this. So, and the IPCC was, if you like, a little bolder with this figure in saying that sustained warming of as little as 1.5 degrees Celsius above pre-industrial could commit up to 30% of the world's species to extinction. And if we go again to 3 degrees Celsius above pre-industrial, up to half of the world's species would be, and this is verbatim, committed to extinction. Okay, so that sort of ends the doom and gloom portion of the talk. There is a bright side to all this, and namely, we know how to get out of the crisis. And the root cause, as I mentioned, 80% of the cause is fossil fuels. And why is that the case? Well, they're the cheapest energy, and the reason for that is basically twofold. They're heavily subsidized to the tune of $500 billion a year globally, and their true costs in terms of human health and environmental impacts and so on are completely externalized. And so the remedy for that is to enact a rising price on carbon emissions. So that's the fundamental requirement, but we also need other things to help us along, namely improved regulations related to efficiency, vehicle efficiency, building efficiency, and so on, and also technology, R&D. And finally, personal and individual actions. These are the things we often hear about, driving more fuel-efficient cars, switching to compact fluorescent light bulbs, eating fewer animal products, and so on. All that stuff will help, but it's far from sufficient. So this really has to be solved within an international policy framework. Okay, so what does all this mean in terms of fossil fuel use? This figure shows the amount of fossil fuels, coal, oil, and natural gas that we've burned so far over the industrial era. That's the regions in purple. And the regions in blue and yellow are the amounts remaining. And you can see that the amounts burned so far amount to a tiny fraction of what's potentially usable. And in fact, recent assessments, like the one shown here, this is something I had compiled for a recent paper of ours, they reveal that potentially usable fossil fuel resources contain dozens of times the amount of carbon in the atmosphere. So if we burn even a significant fraction, any significant fraction of the remaining, especially coal or unconventional oil or gas, we're in deep trouble. As Mark mentioned, among other reasons, because CO2 has a multi-millennial lifetime in the atmosphere. So this implies that the remaining fuels, again, especially coal and the unconventional fuels, must not be burned unless the resulting CO2 emissions are captured and sequestered. But unfortunately, the technology to do that is still in its infancy, and so it's unlikely to make a significant dent in the near term, in the relevant time frame. So again, on the bright side, there are good examples of rapid emissions reductions, even in high energy using countries. So for instance, in a single decade, from the late 70s to late 80s, France increased its nuclear power output by a factor of 15, and that resulted in the fraction of its electricity coming from nuclear increasing from 8% to about 70%. And similarly, in Germany, over the past 15 years or so, we've seen a significant increase in the share of electricity from solar and wind, and a slight decrease in fossil fuel share of electricity. And they've also halved the share of electricity from nuclear. That's not necessarily a good or a bad thing by itself, but the problem the problem's arisen in the last few years because they decided after Fukushima, I'll get into more details about this later, but to rapidly phase out some of their nuclear power plants, and that's led to an increase in their coal emissions in the last couple of years. Okay, so on to a focus on nuclear power as a mitigation option. So here I'm mainly going to be talking about a...
That is a law school thing.
Okay. Someone wants me to rush, I guess. Okay, so here I'm going to be talking about a peer-reviewed scientific paper that I published with Jim a couple of years ago in the journal Environmental Science and Technology. And I got the idea for this paper after witnessing the widespread backlash against nuclear after Fukushima, which occurred in March 2011. Given the extensive focus on the drawbacks of this energy source, I wanted to conduct a big picture, objective, long-term analysis of its potential benefits in terms of human health and climate. So, okay. So for starters, I mean, we have to acknowledge that, again, being objective, there is no perfect energy source. Nuclear has its pros and cons. But because it supplies a significant fraction of world electricity, it's de facto a very important low-carbon, low-air pollution energy source. So to conduct our analysis, we started with a simple thought experiment. What if nuclear power never existed? What energy sources would have replaced it, and what are the implications of that replacement? So we looked at several different spatial scales. Besides the world as a whole, we also looked at OECD Europe, which in this case includes 13 countries, and the recent top 5 CO2 emitting countries. And together, the subglobal regions we analyze account for about 90% of world nuclear energy production. We also looked at 2 different time periods, the historical period, which covers about 40 years, and the projection period from 2010 to 2050. So
I think you have to go one forward and one back, Pushker. Something wrong with it.
All right. So, okay, so for the historical period, we need to start with several pieces of information to address this thought experiment quantitatively. So we started with the annual nuclear energy production data. These are data from the IEA. The nuclear production numbers are shown in red here. And we devised a capacity factor-based substitution scenario, where capacity factor is defined as the ratio of actual power output to the theoretical output for whatever electricity generating device you're talking about, whether it's a wind turbine, a nuclear reactor, and so on. I won't get into the details, but so on a global basis, this gives us about 95% replacement of historical nuclear by coal and the remainder by gas. And this level of substitution by coal is fully plausible for basically the same reasons coal has been by far historically the largest source of electricity, namely its low fuel and total production costs, its high capacity and high capacity factor, and very importantly, the fact that it's a widespread and abundant resource. You can see the curve for coal here is far greater than any of the other curves. Right, so for the projection period, we started with slightly different data. We took the range of annual nuclear energy production from an expert assessment conducted by the International Atomic Energy Agency. And this assessment does account for the effects of Fukushima on energy choices. So the high-end curves shown here reflect aggressive climate mitigation policies, and the low-end assume essentially none. The choice of substitution scenario in this case is a bit more complicated. Unlike with the historical case, there are other alternatives that could replace nuclear besides just coal, or besides most likely coal, namely advanced high-capacity factor gas plants, which can act as baseload power plants, and possibly some types of renewables, for instance, concentrated solar power plants with large-scale thermal storage. These other energy sources have also become more competitive with coal in terms of baseload power. And to simplify these complexities, we just decided to do a bounding analysis where we looked at two extreme cases, one in which all projected nuclear all of these nuclear production values are replaced by coal, and the other in which it's all replaced by gas. So again, because there are other alternative replacements that we could have looked at, for instance, renewables, which wouldn't have yielded too much interesting because they have more or less similar mortality and emission factors as nuclear. And in any case, our results for the projection period should be regarded as upper and lower limits. Okay, so due to the actual calculations, we used the published peer-reviewed mortality and greenhouse gas emission factors shown here. And these are defined in terms of the deaths and emissions per unit electric energy produced. And I want to stress that these values all reflect impacts over the entire life cycle for each fuel source. So that includes fuel mining, transport, waste disposal, plant construction, and so on. And except as noted for China, the mortality factors and the emission factors actually are based on analysis of developed countries. And the mortality factors shown here reflect the sum of deaths from occupational accidents and air pollution-related deaths. So in the case of nuclear, for instance, air pollution-related deaths implies deaths from radiation fallout. So just looking at these numbers alone, it becomes immediately clear that per unit electric energy, nuclear causes 400 times fewer fatalities and 16 times lower greenhouse gas emissions than coal, and about 40 times lower fatalities and 9 times fewer greenhouse gas emissions than natural gas. And our emission factors are a few years old now, but they're still fully consistent with the range of emission factors given in the latest IPCC report, which is shown here. So you can see from here that the values for nuclear, again, this is greenhouse gas emissions per unit electric energy produced. The values for nuclear are broadly similar to the values for the non-hydro renewables. So finally, using all this information to do the actual computation of net prevented impacts by nuclear, we looked at, for each year of each substitution scenario, we calculated the prevented impacts as the difference between the impacts caused by the replacement fossil fuel and the impacts caused directly by nuclear itself. So what we find is pretty staggering, especially in terms of prevented mortality. So this figure shows prevented mortality, net prevented deaths for both the historical and the projection periods for all the regions that we looked at. And what we find is that in the historical period, nuclear prevented an average of about 2 million deaths globally. And over 500,000 deaths, again, these are cumulative net deaths prevented, over 500,000 deaths in each of Europe and US, and over 150,000 deaths in the former Soviet Union and Japan. And in the projection period, the numbers are even more staggering. We find that on the global scale, nuclear, depending on which fuel it replaces, it could prevent between 400,000 and up 7 million deaths out to 2050. And I should point out that on these mortality numbers, there's a significant error bar, and this reflects the 95% confidence interval of the mortality factors that we used, and it's roughly a factor of 4 above and a factor of 4 from the mean. Also, I haven't shown this here, but we also looked at prevented serious illnesses, and the numbers aren't too important to show here because they're basically a factor of 10 higher than these. So nuclear has clearly contributed hugely in terms of prevented mortality and prevented morbidity. So this figure shows our results for prevented mortality on an annual basis. So we see from here that in the previous decade, nuclear on average globally prevented close to 80,000 deaths per year, and over 20,000 deaths a year in Europe and the US, and several thousand in the other regions we looked at. Okay, so our results for prevented greenhouse gas emissions are equally stunning. We find that in the historical period, which is shown on the top bar graph here, on the global scale, nuclear prevented on an average of about 64 billion tons of CO2 equivalent emissions globally, and that's massive. That is equivalent to the CO2 emissions output of several hundred large coal-fired power plants, or to put it another way, it's equivalent to the cumulative CO2 emissions from the past 35 years of coal burning in the US, or the past 17 years of coal burning in China. And the projection period, again, the numbers are even more impressive, because nuclear could, again, depending on which fuel it replaces on the global scale, it could displace up to 80 to 240 billion tons of CO2 equivalent emissions. Right, so as with any theoretical analysis, it's useful to compare to the real world when possible. So let's do that for mortality. So for reference, our calculations give us almost 5,000 deaths cumulatively caused by nuclear in this historical period. This is significant, but it's still several hundred times lower than our calculations for prevented deaths. And what about the empirical data? What can we tell from those? Well, we analyzed each of the 3 major nuclear accidents, starting with 3 Mile Island, which was in March of 1979. And we find that there have been a number of investigations, very thorough scientific by both federal and state agencies and independent academic groups, and they all come to more or less the same conclusion, namely that there is no significant radiological impact from 3 Mile Island to either people or the environment. For instance, here's a study that looks at, it was a 20-year follow-up study looking at a cohort of over 30,000 people that were affected, and they found no attributable deaths due to cancer from the radiation fallout. Now, what about Chernobyl? That's the most controversial one because it's the only accident in the 50-plus years of commercial utility-scale nuclear power generation that has led to scientifically attributable fatalities due to radiation fallout. And by far the most comprehensive, authoritative scientific assessment I found of this is the 2008 UNSCEAR report. So UNSCEAR is the UN Scientific Committee on the Effects of Atomic Radiation. And they're much like the IPCC in that they conduct a critical synthesis and review of droves of peer-reviewed scientific sources, and they analyze 20 years of data for various illnesses. What they find in terms of mortality is that 28 first responders died within a few months of the accident, and those deaths were directly attributable to radiation because they're acute radiation sickness. And a further 15 deaths occurred because of thyroid cancer, which again is attributable to radiation fallout. And those 15 deaths from thyroid cancer were out of 6,000 diagnosed cases. So the actual incidence of deaths from thyroid cancer, and this is not to diminish the suffering of anyone with thyroid cancer, obviously, but the fact is it's a highly treatable disease. Other than that, the assessment found possibly elevated rates of leukemia and cataracts in a relatively small fraction of the several 100,000 recovery workers. Otherwise, they found no persuasive evidence of any other health effects due to radiation fallout from the accidents, except psychological trauma. This includes stress, fear of radiation, and so on. And that is significant. That has changed the quality of life for many of the residents there. Furthermore, the authors chose not to quantify projected deaths because of what they considered unacceptable levels of uncertainties in the predictions. So when you hear figures like, oh, there's likely to be tens of thousands or even hundreds of thousands of deaths in the future from Chernobyl, you should be highly skeptical because it's very difficult to quantify those meaningfully and to convey all the uncertainties in the predictions that are used to derive them. Okay, in terms of ecological impacts, the International Atomic Energy Agency in 2006 conducted an assessment that found that they were worst in the initial few years after the accident. But even then, they were mostly isolated to what's now the Chernobyl exclusion zone, which is a 30-kilometer radius around the plant. But fast forwarding to recent history, the biota there, including within just a few kilometers of the plant, is flourishing. And part of the reason, ironically, is because of the evacuation of all the humans. So, as far as aquatic ecosystems, contamination of water bodies was worst within the first few weeks after the accident. But now the only concern remaining are a few isolated lake systems. Okay, what about Fukushima, which is the most recent accident? UNSCEAR again conducted an assessment of this accident, and it published the reports almost exactly a year ago. This report reflects the scientific consensus of over 80 technical experts from 18 different countries. And I won't get into the details, but the upshot is they found, as with 3 Mile Island, no significant observed or expected impacts for humans or ecosystems, except a theoretically increased risk of thyroid cancer among the children who are the most exposed. All right, what about comparison to empirical data with respect to greenhouse gas emissions? This figure shows, it's a little busy, but it shows the electricity production by 4 select sources in Japan and Germany over the last 20 years. And I highlight these 2 countries because they made decisions directly after Fukushima that affected their nuclear power output. Namely, they phased down a significant number of their nuclear reactors. In the case of Japan, you can see nuclear, which is the blue curve here, plummeted to near zero. And that's understandable. But in Germany, they also decided to phase down their nuclear by a slightly less amount. So the upshot of this is that in the years since Fukushima, generation of electricity from fossil fuel sources has increased significantly in both these countries. So in Japan, fossil fuels, coal and gas, shown here, amount to about 70% of electricity generation. And in Germany, coal amounts to about half of electricity, almost half of electricity generation. Whereas renewables, while they have shown an impressive increase, the renewables in Germany are the dashed line here. Since Fukushima, they've increased marginally, but it appears that the increase went mostly in replacing gas, which decreased concomitantly. And despite all that we hear about Germany, and it is impressive, but the fact is, on an annual basis, it's important to integrate out the noise that we see. So, in other words, we hear a lot of headlines and so on about Germany in the summer generating upwards of half of its electricity from solar and wind and so on. But what really matters is the longer-term generation. And when you look at it in that sense, solar and wind combined in Germany in 2013 accounted for just under 14% of total electricity production, whereas again, coal still remains dominant by far. And so the upshot of this with respect to greenhouse gas emissions is that since Fukushima, CO2 emissions in Japan have increased by 7% in the year after Fukushima, and then they remained at that level in 2013. And in Germany, they increased by 3% in 2013 and another 2% in 2012. These might not seem like large numbers, but to put them in perspective, the CO2 emission, the global CO2 emissions increase over the last decade has been about 3% per year. So these are significant increases. All right, so I think I'm running out of time, but basically we acknowledge in our paper, you can read there for more details, but that there are various uncertainties and limitations to our study. As with any scientific analysis, they mainly stem from the fact that our mortality and emission factors are time invariant, and they also don't reflect the substantial disparities between developed and developing countries, nor do they reflect the impacts of ongoing climate change in the case of the emission factors. Okay, so to summarize, significant problems obviously remain with the current generation of nuclear power, but it has clearly made major contributions to mitigation of human-caused climate change as well as air pollution, which, by the way, I didn't mention it, but I think we heard some statistics earlier from the World Health Organization, but the latest estimate actually puts the number globally for outdoor ambient air pollution-related deaths globally is almost 4 million, and about 1 million of those occurred in China alone. So air pollution is a massive problem, along with climate change. So nuclear, in the historical period, nuclear has likely prevented hundreds of thousands of times more deaths and 15 times more greenhouse gas emissions than it's caused. And in the next few decades, it could prevent millions of additional deaths and hundreds of billions of tons of emissions if it replaces coal. And as a sort of corollary to our assessment, we find that a large-scale expansion of natural gas, if it's unconstrained, meaning if the resulting emissions aren't captured and sequestered, would cause far more deaths and greenhouse gas emissions than a similar expansion of nuclear power. And that stems simply from the higher impacts per unit energy that I discussed earlier. Okay, thanks a lot.